Could a monster earthquake sink a portion of Northern California?
A catastrophic earthquake in the Pacific Northwest would topple buildings and bridges, not to mention the damage from a tsunami.
A sudden and unexpected series of events on the ocean floor has ignited a wave of concern among geologists and seismologists around the world. The focus is the Cascadia Subduction Zone, an immense, ominously quiet fault line stretching from Northern California to British Columbia. It is a region long known for its potential to unleash catastrophic megathrust earthquakes. But now, new and perplexing movements beneath the seafloor have pushed the scientific community into high alert. In recent months, advanced ocean bottom seismometers and GPS arrays have picked up unusual seismic tremors, rapid crustal deformations, and an unexplained shifting of the sediment layers, phenomena that point to something far more complex and possibly more dangerous happening below the surface than previously understood. Before we start, smash the like and subscribe buttons for more updates. At the heart of the matter lies the mounting evidence of accelerated tectonic creep, a type of slow and steady movement that typically flies under the radar because it doesn't produce the jolts and ruptures of a typical quake. But this time, the movements are anything but ordinary. Instruments anchored deep in the Pacific Ocean along the subduction interface are registering accelerations in strain accumulation rates, in some areas showing patterns that suggest the tectonic plates are locking and unlocking in strange rhythms. These patterns are not only unprecedented in their intensity, but they are also occurring in segments that have historically been considered seismically dormant for centuries. For scientists monitoring this region, the data is more than unsettling. It challenges long-standing models about how strain builds and releases along the Cascadia Subduction Zone. One of the most alarming findings came from a seafloor observatory off the Oregon coast, where pressure sensors detected an abrupt vertical displacement of the ocean bed, an uplift of several centimeters that occurred in mere hours. While small in absolute terms, this kind of rapid movement is unusual and typically associated with pre-seismic or even co-seismic activity, suggesting that the fault could be priming itself for a release of built-up tension. Combined with other anomalies, such as increased heat flux, minor fluid seepage through fault lines, and shifting patterns of microseismicity, this singular event now appears to be part of a wider, more complex transformation unfolding beneath the sea. These recent developments have shattered the illusion of predictability around the Cascadia region. For decades, the lack of major earthquakes here lulled many into a false sense of security. But experts have always known that Cascadia is capable of generating magnitude 9.0 or higher earthquakes, rivaling even the most destructive tremors recorded in human history. What is different now is the nature of the warnings. Instead of sudden jolts, the Earth is whispering through cryptic movements and irregular signals, a quiet subterranean language that is difficult to interpret yet impossible to ignore. The shifting behavior suggests that the boundary between the Juan de Fuca and North American plates is entering a new phase of activity, one that may redefine the tectonic risk profile for the entire Pacific Northwest. Adding another layer of urgency is the fact that the changes are happening across multiple segments of the subduction zone simultaneously. Typically, tectonic activity clusters in confined areas, giving scientists time to isolate and understand the causes. But in this case, sensors across hundreds of kilometers, from Northern California to southern British Columbia, are detecting a cascade of strange behaviors. From spontaneous slow-slip events to bursts of deep tremor activity known as episodic tremor and slip ETS, the region seems to be undergoing a synchronized awakening. This synchronicity, while not fully understood, raises the specter of a much broader tectonic realignment, potentially leading to a large-scale rupture. For scientists, the most disturbing part is not just the movements themselves, but their implications for the underlying stress regime. The models they have relied upon for years suggest that stress accumulates in relatively linear patterns, gradually building up to a breaking point. Yet the recent data indicate a more volatile environment, where stress may be transferring erratically between segments, influenced by fluid dynamics, sediment composition, and perhaps even deep mantle processes. If this is the case, it means the fault could behave in unpredictable ways, making it much harder to forecast the timing and size of future quakes. These revelations have triggered a frenzy of activity within the scientific community. Researchers are scrambling to reprocess decades of seismic and geodetic data, looking for overlooked patterns or early signs of the current shift. Sophisticated 3D models of the fault zone are being updated to account for the newly discovered movements. International collaborations are forming at an accelerated pace, with teams from Japan, Chile, and New Zealand, regions that have endured similar megathrust quakes, offering insight into possible trajectories for Cascadia. The common consensus emerging from these efforts is that the situation is highly unusual and possibly unprecedented in the era of modern instrumentation. At the microscopic level, the subduction interface is a dynamic battleground of mineral deformation, pressure gradients, and fluid migration. Under typical conditions, water-rich sediments carried by the subducting Juan de Fuca plate are slowly dehydrated as they descend into the mantle. This dehydration releases fluids into the overlying plate, which can lubricate the fault and either promote or inhibit seismic slip, depending on their concentration and distribution. Recently, however, anomalies in fluid pressure measurements suggest that this system is not functioning as expected. Some sensors have recorded abrupt increases in pore pressure, potentially destabilizing the interface and making it more prone to rupture. Meanwhile, ocean bottom hydrophones have picked up strange acoustic signals, low-frequency rumbles and moans emanating from the deep, accompanied by brief bursts of harmonic tremor usually associated with magma movement or hydrothermal activity. While no direct evidence of magmatic intrusion has been found, the presence of these acoustic emissions adds yet another layer of complexity to the unfolding scenario. Could it be that the Cascadia system is experiencing interactions between tectonic and magmatic processes? If so, the risk calculations for the region may need to be rewritten from the ground up. Further complicating the picture are the subtle yet far-reaching impacts of climate change on oceanic and tectonic systems. Glacial melting and sea level rise are altering the distribution of mass across the Earth's surface, creating what are known as glacial isostatic adjustments. These shifts can affect the stress balances on tectonic plates, especially in regions like Cascadia that are already delicately poised on the brink of rupture. Some researchers now believe that the observed seafloor movements may be partially influenced by these large-scale environmental changes, effectively nudging the fault toward instability. There's also the matter of sediment loading. Recent underwater mapping missions have revealed a surprising accumulation of sediment on the Cascadia accretionary wedge, a thick pile of oceanic mud and sand scraped off the subducting plate. This sediment plays a dual role. It cushions the fault interface and stores pore fluids, but it can also act as a trigger under the right conditions. If enough pressure builds up beneath these layers, it can suddenly be released, allowing the fault to slip more violently. The recent seismic noise and ground deformation could be symptoms of exactly such a process unfolding in real time. This mosaic of signals, each fragment offering a glimpse into the inner workings of the subduction zone, has created an atmosphere of anxious anticipation among those who study Earth's most powerful forces. There is a growing realization that something fundamental may be shifting beneath Cascadia. Whether it is a harbinger of a major seismic event or the beginning of a prolonged period of tectonic volatility remains uncertain. But what is clear is that the zone is no longer behaving in the quiet, predictable manner that allowed communities to plan, build, and live with a sense of relative geological calm. The psychological impact on the scientific teams observing these developments cannot be understated. These are individuals who have devoted their careers to understanding the Earth's behavior, often with the hope of providing early warnings to mitigate disaster. But the current scenario defies many of their assumptions. The fear isn't rooted in what has already happened, it's in the unknown trajectory of the movements now underway. Every new data feed, every recalibrated sensor, and every anomaly logged is a reminder that nature is always a step ahead, operating on scales and principles that remain only partially understood. Adding further urgency is the dense population centers that lie directly in harm's way. Cities like Portland, Seattle, Vancouver, and even San Francisco sit atop ground that could liquefy or collapse if a major rupture occurs. The coastal lowlands of Washington and Oregon could face tsunamis within minutes of a full margin rupture with little time for warnings. And yet, despite decades of research, the precise mechanics of how and when this subduction zone will rupture remain elusive. The new seafloor movements may not just be warning signs, they could be the beginning of the final approach. Across the Pacific Northwest, agencies are now closely watching these tectonic breadcrumbs. The regional network of seismic sensors is being expanded, Deep-sea observatories are being deployed and reinforced. Autonomous underwater vehicles are performing continuous surveys of the ocean floor, checking for new deformations or chemical changes in seafloor emissions. The effort to understand what is happening has moved into overdrive, not just out of scientific curiosity, but because the stakes are profoundly real. What's occurring beneath the waves could dictate the future of millions of lives on land. Amid this flurry of scientific activity is a sober reckoning with the limitations of current forecasting capabilities. The Cascadia Subduction Zone has always been a difficult system to model, largely because its last major rupture occurred before the age of modern instrumentation in January 1700. That quake, which likely registered close to magnitude 9.0, sent a massive tsunami across the Pacific, impacting Japan. But beyond historical and geological records, there has been little direct observational data, until now. These new movements may be the first real-time glimpse into the build-up phase of another major Cascadia event, a terrifying possibility that adds both gravity and urgency to every new discovery. The mounting sense of alarm among scientists isn't driven by hysteria, but by data, by cold, hard signals transmitted from the deep sea to labs and offices where algorithms churn and experts pore over graphs with furrowed brows. The warnings are not sirens, but subtle shifts, minute tremors, and unexpected displacements that together paint a picture of a system straining at its limits. The Earth is not quiet beneath Cascadia anymore. It is stirring, murmuring through stone and sediment, and those trained to listen are now hearing a tune they never expected to hear in their lifetimes. There is a growing consensus that the Cascadia Subduction Zone may be transitioning into a new state of tectonic activity. Whether this transition results in a rupture tomorrow, next year, or decades from now is still unknowable. But the evidence of movement, widespread, strange, and accelerating, is undeniable. Something is happening beneath the Pacific Northwest, and for those watching the data pour in, there is no longer any doubt. The sleeping giant beneath Cascadia is beginning to stir, and the countdown to its next great release of energy may already be underway. Even as the signs from the seafloor become increasingly complex, the depths of the Cascadia Subduction Zone continue to withhold their full story. The most recent developments have captured the attention of deep marine geophysicists, who now suspect that the anomaly may be rooted in more than simple plate movement. Layers of the Earth's crust, once thought to be stable, are showing signs of plastic deformation, slow, non-brittle warping under pressure, suggesting that deeper zones of the interface may be behaving differently than previously imagined. Unlike brittle fractures that release tension suddenly in earthquakes, plastic deformation can silently redistribute energy within the lithosphere, potentially creating unstable pressure pockets elsewhere along the fault line. This behavior hints at a new conceptual model where different segments of the subduction zone may be operating on separate mechanical rules. At shallow depths, where temperature and pressure conditions are lower, ruptures may occur suddenly and catastrophically. But further down, in the hot and ductile zones beneath the crust, strain may accumulate silently before being transmitted upward in unpredictable bursts. These mismatched behaviors could make the Cascadia Subduction Zone especially treacherous, as stress released deep below might cascade upward, triggering shallow quakes and eventually leading to a full margin rupture. The implications of such a model are far-reaching, potentially altering how early warning systems interpret slow tremor and fluid migration patterns. In this evolving picture, one area of interest that's emerging is the plate interface zone near what's called the locking line, the boundary between the zone that is stuck and accumulating stress, and the zone that is creeping and releasing energy slowly. Historically, this transition area has been overlooked in favor of the high-energy stuck zones, but the latest data suggests it could play a decisive role in how ruptures initiate and propagate. In particular, researchers are closely examining the patchiness of locking along the fault. Some sections are tightly coupled, holding back massive amounts of energy, while others are slipping steadily or even showing signs of relaxation. This heterogeneity means that rupture propagation, once it begins, might not be smooth. It could jump erratically between segments, increasing the likelihood of an unexpectedly wide or high-magnitude event. Adding yet another layer of mystery are unexpected chemical signatures in fluid samples collected from the ocean floor. Instruments placed within boreholes drilled deep into the fault interface have recorded a sudden spike in certain isotopes, such as helium-3 and boron, which are typically associated with deep Earth processes. These isotopic signatures suggest that the fluids now venting through the sediment layers may be sourced from much deeper within the Earth than previously assumed. The presence of such geochemical anomalies often indicates high-pressure conditions that can destabilize rock masses, further increasing the chances of sudden fault rupture. The role of fluids in earthquake mechanics cannot be overstated. They act as lubricants, decreasing the effective stress required to initiate fault slip. But they can also cause hydraulic fracturing, increasing pore pressure to the point of weakening the rock itself. With large quantities of these fluids now migrating toward the surface, evidenced not just by chemical markers but by subtle temperature anomalies and increased venting, the fault environment is becoming significantly more dynamic. In essence, the Cascadia Subduction Zone is no longer a dry, locked slab of rock. It is an evolving, fluid-saturated system in which the rules of tectonic engagement may be undergoing rapid change. One particularly compelling line of inquiry has emerged from ultra-deep sonar mapping of the seafloor. High-resolution acoustic imagery has revealed previously undetected fault scarps, steep breaks in the ocean floor surface, which appear to be relatively recent in origin. Some of these scarps span several kilometers and suggest vertical displacements that cannot be accounted for by known historical events. If these scarps are the surface expressions of deeper fault movements, it would mean that parts of the subduction zone are actively deforming in ways that have gone unnoticed until now. This would also imply that the system may be far more seismically active beneath the ocean than current land-based networks can detect, underscoring the need for expanded deep-sea observation networks. Another area now under scrutiny is the sediment compaction behavior in the accretionary prism, the wedge of sediment built up at the edge of the overriding plate. As tectonic forces press this prism against the subducting slab, it undergoes compaction and deformation. However, new data indicate that compaction rates in certain regions are accelerating, a possible precursor to sudden slumping or even submarine landslides. These landslides, while destructive on their own, could also displace large volumes of water and trigger localized tsunamis, independent of or preceding a larger seismic event. The possibility of these cascading hazards occurring in tandem has pushed hazard models into a state of rapid revision. While much of the focus has been on mechanical and chemical processes, electromagnetic studies are now adding a completely new dimension to the puzzle. Recent magnetotelluric surveys, techniques that use natural variations in the Earth's magnetic field to probe subsurface conductivity, have shown anomalous signals in the same regions experiencing rapid seafloor movements. These conductivity changes are believed to correlate with zones of increased fluid content or partial melting, both of which would significantly alter how stress is transmitted through the rock. Intriguingly, some of these anomalies align with the zones of recent microseismicity, suggesting a complex interplay between electromagnetic, mechanical, and thermal processes deep within the fault zone. To better understand this interplay, researchers have begun simulating the subduction zone as a multi-layered system with fluid reservoirs, variably locked zones, and deforming mineral interfaces. These high-performance simulations incorporate everything from mineral physics to heat transport models, and the early results are sobering. They suggest that once a critical threshold of strain, fluid pressure, and temperature is crossed in multiple layers simultaneously, the fault could rapidly transition from stable sliding to runaway rupture. Even worse, this transition could be largely invisible to standard surface-based monitoring systems until it is well underway. The fault's behavior is also being reassessed in light of gravitational anomalies detected in satellite data. Instruments that measure minute variations in Earth's gravitational field have picked up small but significant changes along the Cascadia coast. These gravity shifts, often indicative of mass redistribution within the Earth, may reflect subsurface fluid movement or deformation of the crust itself. While subtle, these signals add to the growing body of evidence that the entire subduction system is undergoing a structural shift, the full consequences of which are still uncertain. As data continues to flood in, a new theory is gaining traction among tectonophysicists, that Cascadia may be entering a period of tectonic unzipping. This scenario envisions multiple segments of the fault unlocking sequentially but rapidly, like a zipper being undone under tension. In such a model, Small releases in one area destabilize adjacent zones, increasing the probability of a full margin rupture. The idea draws from recent observations of complex quakes in other subduction zones, such as the 2011 Tohoku earthquake in Japan, where multiple fault segments ruptured in quick succession, amplifying the quake's energy release and tsunami generation. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on strange seafloor movements recently discovered at Cascadia Subduction Zone? We want to hear from you. Thank you for watching and see you next time.